Hello everyone, in this video we move on to chapter 3 of the textbook, which deals with the problem of estimation. And in this video we'll be looking at how we use regression models to estimate the parameter values beta 1 and beta 2. Now in a previous video I said that what we do when we estimate a regression line is we compress bunch of data points onto a single line, like that. But now the natural next question is, how on earth do we do that? How do we decide specifically what the values of these estimators are? What should beta 1 be and what should beta 2 be? How do we decide those values? Now it turns out there are several ways of doing that. But for a lot of applications, the regression line which minimizes the sum of squared residuals is the one that is best used for this purpose. So what this means is we want to find beta 1 hat and beta 2 hat such that the value of this term, the sum of squared residuals, is as low as possible. And it turns out that these two estimators on this slide, that's the estimator for beta 2, here's the estimator for beta 1, do exactly that. When we apply these two estimators, we are finding values for beta 1 hat and for beta 2 hat such that this term is as small as possible. And if you want to know why that is true, you can look at the lecture notes for the derivation of these two estimators. So what does this look like graphically? Well, here you have a y variable on the vertical axis, x variable on the horizontal axis, and you have a set of data points that map out some relationship between x and y. So the data are all of these dots over here, and some of them are highlighted. For example, this one over here. So the error, or well, the residual in this case, will be the difference between the estimated regression function, which is the SRF given by this line, and the value of this particular yi. So this gap between the yi in this case, well, let's call it y1, since we have u1 over there. The difference between y1 and the value for the SRS at x1, importantly, is given by u hat 1 over here. So that's the deviation between the sample regression function and the observed data when x equals 1. And you can go on to look at the deviations for each of the different x values. There's x2, x3, x4. And what our regression model does, what our estimators do is takes these deviations, squares them, and then minimizes that squared value. And that's how it finds values for beta 1 hat and beta 2 hat. Now the regression line has several properties, which include the fact that it passes through both the sample means of y and x, and that can easily be seen from the specification for the beta 1 estimator. The second property is that the mean of the estimated y values is equal to the mean of the observed y values. And you can look for the derivation of that in the lecture notes. The third important property is that the expected value of the residuals is equal to 0. And of course this follows directly from the fact that this holds. The fourth property is that the residuals are uncorrelated with the predicted y values. And the fifth property states that the residuals are uncorrelated with the independent variable. We'll not bother to derive these last two properties at this stage. Now this slide just shows you how to use these estimators to estimate a regression model based on a set of data. So here you're given data for two variables, variable x being study hours and variable y being final mark for some course. And these are all the data points for both of these variables. Now, to estimate the regression model, all you have to do is plug values into these two formulas. But not all of the values are easily found. In fact, we have to do a few calculations. So the first calculation we'd want to do is to find the sum of x, y, this term over here. So to do that, we multiply each x value with its corresponding y value and then determine the xy value, that is the product of each x and y. Important that you take the y and x that correspond with each other, so you can't take that, for instance. And then we can fill out this column, and when we sum all of these values together, we obtain some number over here, and that then becomes this term over here. For x2, for x squared, we simply square all of the x values. So we simply take, let's call this x1, x1 equals 1, therefore x1 squared equals 1, and so on and so on. Let's look at x3, for example. You can call that x1, x2, x3, etc., etc. And given that there are 10 data points, this last one will be x10. So x3 is equal to 2, therefore x3 squared is equal to 4. We do that for each of the x values and then sum them all together, and the value there will then correspond to this term over here. N is just the number of data points that we have, number of observations, and of course x bar and y bar are respectively the means for x and y. And that is found by dividing the sum of x and the sum of y respectively by the number of observations, n, which in this case is 10. N equals 10 in this example. Okay. So once we've calculated all of these values, we can just plug them into the beta 2 hat formula, and we obtain this expression over here, and simplifying we arrive at this value for beta 2 hat. Now, given that value, we just plug that into our beta 1 hat formula together with x bar and y bar to obtain a value for beta 1 hat given by 22.2385. So a regression model looks something like this. Y hat equals 22 point, I'll just round down to 1 decimal, and plus, notice that we have a positive beta 2 value, so it's plus 6.7, let's make it 6.8 x, and that is our regression model with our estimated values, beta 1 hat 22.2 and beta hat 2 6.8. Okay, so how do we interpret this? Well, for a 1 unit change in x, we observe a 6.8 unit change in y. Now, in the context of the data that we have, we're looking at study hours and its effect on final mark. So for each additional hour studied, a given student's final, on average, again, notice we are estimating, remember that we are estimating the expected value of y given some value of x. So on average, for each additional hour studied, a given student's final mark will increase by 6.8 points. I'm assuming these are percentage points here. So that's how we would interpret the slope parameter. The intercept parameter we interpret as follows. If x is 0, then y, the expected value of y on average, is 22.2. So again, in the context of the data that we have, if a student does not study at all, on average, we would expect them to obtain a final mark of 22.2. And graphically, this is what our regression model looks like. So the blue diamonds are all of the data points, the joint values of x and y, and the red line is our regression function, our SRF, sample regression function. Now looking at this model, we can make some predictions, understanding that it's not precise, of course, but we can ask ourselves, if a student studies for 5 hours, and let's assume this is study time per week, if a student studies for 5 hours per week, on average, what would we expect their final mark to be? And we can just sort of look up, map off of the regression line from x to y, and we'll notice that they'll achieve a pass mark of somewhere between 50 and 60%. We can also go the other way. We can for instance ask a question: if a student wants to achieve a final mark of 75%, then on average, how long should they study for per week? And if we do that, we just map again from y off the regression line onto x, and we see that a student will have to study for about 8 hours per week if on average they are expected to achieve a distinction of 75%. Now we can also use the regression model to find the error terms for each x value. So recall that, well, not the error term, the residual. Recall that y minus y hat, let's just write it out in symbols, yi minus yi hat is equal to ui hat, that's the residuals. And we can find these by using the values in the second and third column on this table. So if we take 30 minus 29, we obtain some value for the residual over here, and we can continue to do that for each x value. Now just looking at the yellows, well, if we consider x, what is this, 10, 9, 8, 7, x7 over here, that is when x equals 4, the y value is, the observed y value is 44, the estimated y value is 49.395. So in this case, we have an overestimation. Our regression overestimates the final mark for a person who has studied 4 hours. If you go back to our graph over here, you can see that that is the case. So here's the observed y value, which is below the regression function. Therefore, our regression function overestimates what someone who studied 4 hours will achieve as a final mark. In the case of someone who studies 8 hours, that is x equals 8, we have an observed value of 80 and an estimated value, y hat, of 76.551. And so in this case, we are underestimating. The regression model underestimates the outcome variable based on the control variable being 8. So if you go back to the regression function again, this is what we observe over here as a y outcome, and our regression model for the same x value of 8 lies over here, just slightly below that. So here we are underestimating the outcome. And that difference between the actual and estimated y values are our residuals. So this table gives you the full list of residuals for all x values in the last column over here. And as expected, based on our properties, the mean value of these residuals equals 0. So recall this was one of the properties of residuals, at least one of the properties of the regression line. So earlier we mentioned some properties of the regression line, and to show you that these properties hold, I'll just use the data we've been working with so far and then go through these properties. So I won't bother with the first one because, as we know, we were able to prove that by just looking at the specification of the beta 1 hat and beta 2 hat estimators. But let's look at the rest of them. So the mean of residuals equals 0. So the residuals are in column D over here. Perhaps I should just put in some headings so you know what you're looking at. So we have the x variable, the y variable. This is the y hat variable, and here we have the residuals. Okay, so we want to check whether the mean of the residuals is in fact 0, as our regression line properties suggest it should be. So if we put in the formula equals average and we select all of the residuals, we do in fact get a value of 0. The next one says that the residuals are uncorrelated with y. So in this cell, I'll just use the Excel's correlation function. So I'll type in correl and then select the predicted y values, which is this column over here, y hat. That's the one argument, and the other argument is then the residuals. So I select all of those. When I press enter, I get a value of 0. And as you know, when two variables are uncorrelated, when the correlation coefficient is equal to 0, which is the case here, or approximately 0. Okay, residuals are also uncorrelated with the x's. So if we again use the correlation coefficient function of Excel, we type in correl, and we select the x values as the first argument in this function, and then the residuals as the second argument in this function. Press enter, and again we see that there is no correlation between x and the x values and the residuals. And then finally, the mean of the y hat is equal to the sample mean. Okay, so we can estimate both the mean, the sample mean of y by typing in average and selecting all the y values. That gives us 46, and we can just drag this formula over, and for the estimated y values we also get a mean value of 46. So all of these properties hold, and they will always hold for every regression model. And that's where we'll leave it for now. See you in the next video where we look at the assumptions of the OLS regression model.